I'm gonna just draw it really fast. I'm not gonna put the numbers on there, but so you got x in feet. Oops. And then this is time in seconds. It kind of starts up here and goes this way, and then it takes off this way. So it's kind of hard to see it because you're looking at a graph.
Right.
But you kind of need to take this. This is just a line stretched out over time. So if you take this and kind of squash it down onto the side, that shows you what the motion actually looks like.
Okay.
And since it's the x-axis, it would actually be something like this. It would start out here, see, like this. And then you can see that it goes down. So it would come back down like this to 0. And it hits 0, and then it takes off this way a little bit faster.
Okay.
Does that make sense?
Yeah.
So you kind of take, time is just stretching it out to show you what it looks like over a course of time. But it's as if this x-axis is just kind of sliding along in terms of time.
Gotcha.
So if you take the graph and just smash it up against the left-hand side, that shows you kind of what it would look like along an actual axis.
Okay, so this is like feet per second, like it's traveling feet per second.
Right, exactly.
Okay.
So this would be its position versus time, but you're right, it's feet per second. So the slope will show you a velocity. So like what you said about pitching. So if you said that like home plate was 0 and somebody pitched it to home and then it gets hit and like the pitch is moving pretty quick, but then the hit is moving even faster as it leaves the bat. So you'd have you have a steeper slope going out this way.
Gotcha. Okay.
But it wouldn't look like this. It's not like the guy is pitching at an angle and then it gets hit out here and he knocks it this way. What actually happens is he pitches from home plate straight in, and it gets hit by the batter and goes straight out.
Okay. Yeah, that makes sense. That helps out quite a bit. So these okay, no, yeah, that makes sense. A lot more sense than. And then with I was confused on making the position versus time graphs compared to the, I think, is it velocity versus time?
Like so velocity versus time and acceleration versus time.
Yeah.
So something I always try to remember, so you're talking about like, now you can see the application of the calculus behind it. So if you got 3 things in physics, you've got position, you've got velocity, and you've got acceleration. These are basically the 3 variables that we just work with over and over again. Even when you get into like 2-dimensional and like circular motion and stuff, you're always talking about position and velocity and acceleration. So if you were to try to go from position to velocity to acceleration using like calculus, say you're given a position equation of like s equals 4t squared plus 3t plus 8, and you wanted to find the velocity from this, how do you think you'd do it?
So this is seconds, right?
Oh, so this is position, so you could say like x or y too.
Oh, okay. That's position.
Yeah.
I guess you have to put the T's or.
So you want to find like the change in x over time, right?
Right.
So that'd be like this, a little tiny change in x over a little tiny change in time. So that's the derivative, right?
Okay.
So if you want to find the velocity, so dx dt equals v equals the derivative of this, which would be 8t plus 3. If you want to find a velocity from position, then you take a derivative. So this is derivative. You've seen, does that make sense to you? Like, have you seen this relationship before as you're taking the class so far?
Yeah, you're talking about it in the class.
Yeah, so if you want to go from position to velocity or velocity to acceleration, then you're taking a derivative.
Right.
And on the graph, that means your slope. It's like you find your rise over run.
Okay.
And then if you want to go the opposite direction, then you're doing an integral, which is basically the opposite of a derivative.
Okay.
And on the graph, that's represented by like the area underneath the graph. It's like this area right here. If you were taking the integral up to this point, you'd find that area. If you're going to this point, you'd find this area plus this area.
So that's the velocity, is that area? Is that what you're saying?
Well, so we're starting with position here.
Position.
So I'm gonna change this, just erase it and redraw it real fast. So we're starting out with a position graph. This is x in feet over time in seconds. It goes like this. And then you want to draw a velocity graph. A velocity versus time graph. So you're starting with position, and you want to find velocity. So according to this, what do we want to do?
With that up there, or
Yeah, so if we're moving in this direction,
find derivative, right?
yeah, so we want to find the derivative. And that's represented on the graph by the slope. So if you can find, so the derivative for this part would be this rise over this run. The derivative over this part would be this rise over this run.
Yeah. Okay.
So up until, let's just draw a little break here. Up until this point right here, what's your velocity?
It's all that shaded in, right? Or that rise over there.
So that would be the integral, right? So that would be if we were trying to go back this way. But we're going from position to velocity, so we want to do the derivative. And so the derivative is basically the slope. And the integral is the area under the curve.
Oh, okay. So it's the slope, so the rise over run.
Yeah.
Okay. And so the slope, so the derivative is the rise over run to the break. Is that what you're saying?
Right, I mean it's the slope, but the slope changes here. That's why we drew a break there.
Right.
So it'll be one value up until this point, and then it'll change
Okay.
because the slope changed.
Gotcha.
So what kind of slope does this line right here have?
Negative.
Yeah, so you know that your velocity, you don't know exactly what the value will be because you don't have any numbers on this graph.
Right.
On the one that you have here, you could find it pretty easily. So like right here, it's 50. So if you went 50 meters backwards in half a second, so then you could say, well, that's 50 over 0.5. So that's your distance. So velocity equals distance over time equals 50 over 0.5 equals 100 feet per second. It's actually negative 100.
Okay.
So right here you have, up until this point, it'd be negative 100 feet per second. So then what about the second part? If you wanna find the velocity there, what do you do?
It's gonna be positive, so. You just, is it still distance over time?
Yeah, so it's rise over run again, and you're
Right.
finding the slope. But because it's a straight line, you can't just use distance over time.
Okay.
So according to your picture, what, well, you don't even know exactly. I guess it goes 100. It's probably at this point, it's at 100 feet after 1 second.
So 100 divided by 0.5?
Yeah. So then the second part, your velocity is distance over time equals 100, this time it's positive, over 0.5. And that's 200.
Yeah.
So then you can come up here and say, well, starting at this point and going out this way forever, your velocity is 200 feet per second.
Oh, okay. So that's the. So to find like the velocity versus time, you just do the distance divided by time. And that tells you like the velocity over time.
Right.
Okay. That's making it a lot harder than
So for this first half a second, it's going negative 100 feet per second. So that'd be like the pitcher throwing it in at 100 feet per second, which I don't know if that'd be I don't know, it's like 100 feet per second. I don't know what that would be in miles per hour, but, and then he gets hit and it takes off 200 feet per second going the opposite direction.
Okay. Okay, that helps.